Hello and welcome to the second part of the lecture on Intel SGX. This is in the course for Secure Systems Engineering, which is part of the NPTEL series. In the previous video, we had also looked at the Intel SGX. We seen what was capable with this particular feature in the processor. We looked at how the processor actually managed the memory, how it actually allocated memory regions for enclaves, how things were actually stored in the enclave, and so on. In this part of the video lecture, we will look at Intel SGX more from a software perspective. We will look at how applications would use the Intel SGX feature, and we create enclaves, what are the instructions that are available for supporting these features. So, a lot of what we are actually talking is present in this particular paper, Innovative Instructions and Software Model for Isolated Execution. This was published in HASP 2013. Also, some of the figures that are in this video have been actually borrowed from Intel. So, a typical application development on a system which has SGX supported would require that you actually split the application into two parts. One is the trusted part, which you want to be part of the enclave, and also the untrusted part, where the remaining part of the application is present. So, the trusted part would be aspects such as cryptography, where a region where passwords are stored, a region where encryption and decryption is done, secret keys are stored, and so on. The remaining part could be the regular application like access, like the graphical user interfaces, other user interfaces, and so on. Note that unlike the trust zone that we have seen earlier, both the untrusted application and the trusted application are present in the same address space. In fact, the trusted part is just mapped to a certain region within that particular application. So, when typically it would be the untrusted part of the application which is executing. The application would continue to execute until there is a call required to move to the trusted app. So, this essentially is a call to the enclave. So, in order to actually incorporate SGX in an application, the application would first need to create an enclave. The application would typically run in a untrusted mode, and occasionally when there is enclave needs to be called, or rather when the application needs to call a trusted function, then there is a switch from the non-enclave mode into the enclave mode. Then the step 3 is where the enclave function executes and processes the security related sensitive data, and finally the mode is switched back from the enclave mode back to the untrusted or the unenclave mode, and the application continues to execute. So, these are the various steps involved when applications are developed with SGX enabled, and the applications have enclaves. In order to actually support this form of application development, Intel has a few instructions. So, these instructions have been added on to the instruction set of the Intel processors in order to create enclaves, invoke trusted functions, and so on. So, we will first look at what these special functions are. So, first of all, these special extensions for SGX are divided into two forms. One, you have the privileged set of instructions and the user level instructions. So, the privileged instructions essentially should be run as a super user, where you have instructions to create pages, add pages, extends pages, remove enclave, create an enclave, and so on. Also, the paging related aspects such as eviction of the page, loading of a page is all done as part of the privileged instructions. The user level instructions, on the other hand, are mostly just 2 or 3 of them. One instruction will permit you to enter into the enclave, another one will permit you to leave the enclave, and a third one would known as a resume would permit an application running in user mode to resume after an interrupt or a exception has occurred. So, let us look at an overview of these various instructions. The first one is to actually create the enclave, that is the ECREATE instruction, and as we see over here, create is a privileged instruction. So, whenever an application wants to create an enclave, it would require to make a system call, and within the system call there would be an ECREATE instruction which would initialize or initiate the enclave creation. So, when ECREATE is invoked, the processor would create an SECS structure in the PRM, the processor related memory, and this SECS structure, as we know before, would contain the global information about the enclave. Now, the unique thing about the SGX is that the operating system can choose and manage where in the entire virtual address space the enclave should be present. For example, the operating system could choose a particular virtual address page and specify to the hardware that the enclave should be created in this particular page. Now, the unique thing about this is that due to the hardware protection mechanisms, this is just choosing the page or the address where the enclave is present is about all the operating system can do. It will not be able to read or write to the contents within that particular page, but rather just manage that page. Also, while creating the page, the operating system would need to specify other aspects such as the operating mode, whether it is 32-bit or 64-bit. It needs to specify the processor features that is to be supported, and also whether debug is allowed or not within that particular enclave. So, after creation is done, the next step is an EADD instruction. So, EADD is also a privileged instruction, and therefore, it can be only done by the operating system. So, as before, when EADD is invoked, the operating system is capable of actually selecting a particular ECS page where the enclave code or data is used. So, typically the operating system would be able to manage this particular page, but would not be able to actually read or write the contents of that page. So, EADD will do two things. First, it will actually initialize the EPCM. So, as we have seen in the previous lecture, every ECS page has a corresponding EPCM entry, that is the ECS page map, which contains essentially the privileges and the access control for that particular ECS page. So, for example, as we have seen, it has the read, write, execute permissions, the addresses, linear addresses that will access that particular page, and also it has some information regarding the page type, such as whether it is TCS or reg or so on. Then done is that EADD completely implemented in the processor will then record EPCM information in a crypto log that is stored in the SECS. So, note that the SECS was created during the ECREATE instruction which was done initially, and during the EADD per ECS there would be some log which gets appended or added in the ECS. Then the ECS is filled, and there is 4 kilobytes of data which is copied from the hard disk, that is from the application's binary to the ECS page, that is to the DRAM. So, note that all of this data is encrypted because this data present in the hard disk as well as the DRAM is present outside the processor, and as we have seen before, any information outside the processor which is any enclave data or code present outside the processor is always in an encrypted state. This ensures confidentiality and could also be used to build integrity. So, after all pages present in the enclave had been added, that is using the EADD instruction. So, for example, if there are like 20 different pages, then EADD would be invoked 20 different times, one for each EPC page present in the enclave. After all of these pages have been added, the operating system would then need to call EExtend. So, the EEXTEND would essentially measure a 256 byte region in an EPC page. So, this region is specified by the developer. The measurement actually comprises of a 64-bit address and 256 byte information present in the SECS. Since we are actually measuring 256 bytes at a time, so therefore, we have 16 invocations of EEXTEND needed to measure the whole page. So, construction of the enclave would actually result in a matching with the enclave owner. So, this is where we actually would obtain some level of integrity, because when an enclave gets created by an application developer, the application developer could actually specify which regions in the various EPC pages should be measured. Also, he could also specify a particular signature for those particular EPC pages. Thus, what is ascertained by the EEXTEND instruction is that the creation of these various EPC pages is exactly similar, or has exactly the same signature as what the application developer intended. So, after EEXTEND, the next instruction that gets invoked is EINIT. So, EINIT is again a privileged instruction and therefore should be done by the operating system. So, it is invoked after all the pages have been added, and essentially it would verify that the signature matches that of the owner signature. So, if EINIT is successful, it allows the enclave to be entered. So, after EINIT, that is the first step which is over here. So, the first step as we seen over here involves the ECREATE, EADD, EEXTEND and EINIT. So, these 4 steps are all done by the operating system, by applications invoking system calls and then requesting the operating system to actually create this enclave. So, after these 4 steps are done, the enclave is ready to use, and then the application could actually use various instructions such as EENTER and EEXIT to enter and leave the enclave. So, we will look more in detail about EENTER, where the untrusted function could invoke a trusted function which is present in the enclave. When the untrusted part of the application invokes EENTER, there are certain things to be actually specified. So, the EENTER instruction needs to know the location within the enclave where the transfer should be done. It should also define something known as an asynchronous exit pointer, which we will actually see a bit later. So, we look at more in detail about the asynchronous exit pointer, and essentially this is related to interrupt management when in enclave mode. So, when the EENTER instruction is executed by the processor would set the TCS bit, the TCS in the enclave to busy, stating that this particular enclave is in use. It would change the mode from the non-enclave mode to the enclave mode. Then it would save the state of the stack pointer, base pointer and so on, and it will also save something known as the AEP. So, these state savings, like the context savings in the stack and base pointer and so on, are saved, so that after returning from the enclave, the normal mode of operation can continue. And finally, there is a transfer from outside the enclave to the to inside the enclave, and if all permissions have been checked are correct, the hardware will permit the enclave function to execute. So, all of these steps are done during the EENTER instruction, and as we have seen, EENTER is a user mode instruction, and therefore, an application, for example, wants to do an encryption, would invoke EENTER to trigger the encryption in the enclave mode. Now, after the encryption is complete in the enclave mode, the application could return from the enclave mode to the non-enclave or the normal mode of operation using the EEXIT system call. Essentially, in this instruction, the processor will ensure that the enclave mode flag is cleared, which will actually indicate that it is going back to the normal mode, and also it will flush the various TLB entries. It will mark the TCS as free, and it will transfer the control from inside the enclave to outside the enclave. Now, typically what is expected is that whenever there is an EENTER instruction, the only way to exit from the enclave is by this EEXIT instruction. However, there are exceptions to this particular case. The exceptions occur when there is an interrupt that occurs when in enclave mode. So, for example, let us say that the enclave mode trusted function, let us say an encryption, is executing, and during this particular period an interrupt occurs. During this time, the processor would require to service the interrupt. Now, this makes things a bit more complicated because interrupts are asynchronous events, and therefore, the processor would need to service this interrupt without compromising on the security of the enclave. So, in order to do this, there is a special technique known as the AEX or the asynchronous exit, which is supported by SGX, and this feature would actually permit interrupts to be handled when in enclave mode as well. So, critical in this asynchronous exit is something known as the AEP, which stands for the asynchronous exit pointer. So, note that the asynchronous exit pointer is actually set up during the EENTER instruction. So, what is done here is that some memory location outside the enclave is actually specified, and the fact is whenever so it would typically point to a function which gets invoked whenever there is a return from the interrupt. So, this deviates from how interrupts are typically managed. So, as we know from earlier classes that whenever an interrupt completes its execution, this is done by the IRET instruction, and the IRET instruction would essentially enforce the previous context, and the program which was executing prior to the interrupt occurring would continue to execute. Here with SGX things are slightly different. Whenever there is the IRET instruction that gets executed, instead of going back directly to the enclave, the function pointed to by this AEP is executed. So, this function would then invoke something known as the ERESUME instruction, and ERESUME instruction would then force the processor to move from the non-enclave space to the enclave space. So, the ERESUME instruction would essentially restore all the registers and so on. Another very important aspect which is supported by Intel's SGX is something known as attestation, where this system can actually prove to somebody else, maybe over the network or another server, that it actually has a particular SGX. So, this is made possible because of the signatures which can be computed up for the enclave, and also the fact that all the information in an enclave is actually encrypted. So, there are two attestation techniques which are possible. One is known as the inter machine and the intra machine. So, the intra machine attestation is in a scenario where there are multiple applications running in a system, and one application having a specific enclave can prove to another application in the same system that it has this particular enclave. So, this is done by the signatures. And the second thing about the inter machine attestation, where as we mentioned before, the application could actually prove to a third party over the internet that it has a specific enclave. This has several applications. You are encouraged to actually look at Intel's POET, that is a proof of elapsed time technique, which is quite a technique for blockchain, where this feature of attestation comes in handy, and machines or systems could actually prove to some other system on the network that it owns a certain enclave and has performed some specific work. So, a lot of this attestation is possible due to a register known as the MR Enclave. So, this MR Enclave essentially uses a SHA-256 hash of an internal log that measures the activity done by the enclave. So, the log contains their various aspects, like it has signatures of the code, data, stack and heap, in the enclave. It has relative positions of the pages in the enclave, security flag associated, and so on. So, the attestation process is will not go into too much detail about this particular process, but you could actually look at this paper titled Innovative Technologies for CPU based attestation and sealing, and this was published in HASP 2015. Thank you.